Okay, so in this picture, which ball will move faster?
The baseball.
Excellent. This is the first class that says the baseball. You guys are obviously the smartest class. The other classes, I think, were being facetious. But yes, you are correct. The baseball will move the fastest. Why? There's several reasons why. Several physics reasons why.
The dude winding up.
Yeah, so the force is greater. Over here, the force is less, right? What else?
I think the baseball is heavier.
The baseball's heavier? It's possible. It's kind of hard to see, but yeah.
Creates more. Since the baseball is heavier, it creates more whip than it would be on the lighter ball.
Gotcha. Yeah. Gotcha. It would create more momentum. But yeah, the mass of the ball definitely is a factor. Okay. What else? So the force is greater, and I think Rob, you said something in the windup, right? So the time that the force is applied is longer, right? So he's applying the force applied longer. Okay.
Well, that wouldn't necessarily
True. So Rob says that doesn't necessarily always mean it's going to go faster. So it's a combination of like how much force is applied and how long that force is applied on it. So if something's moving slower, that's basically going to be a slower force, right? Because force is proportional to acceleration. So if you have less acceleration, you're going to have less force, right? Does that make sense? Yeah, good point. Okay, so yes. So here, the baseball will move faster. We're talking about impulse. Impulse is when you apply a force over a period of time. And this is showing examples of when an impulse causes something to gain momentum, like it gets faster, right? Okay. You can also experience an impulse that slows you down. Okay, here's an example of an impulse that might slow you down. Let's say you're in a small, like electric EcoSmart car and you're driving and your brakes stop working. You have to choose whether to run into a haystack or a brick wall to stop. Which do you choose? The haystack, okay? The brick wall would be very abrupt, it would be very sudden, and it would hurt, okay? Okay, so impulse is a force applied over a certain amount of time. So here's an equation. You're gonna learn, technically it's 2 equations, but we can make 3 equations out of it, but impulse is force times time, okay? If you have a brief force applied over a short time, it produces a small change in momentum. If you apply the same force over a longer time interval, it'll have a greater change in momentum, right? If you push the same force for twice the time, you're going to impart twice the impulse and produce twice the change in momentum. So this is an equation you need to know. Okay, so the greater the impulse, when you apply a force over time to something, when an impulse is applied to an object, it results in a change in momentum. Okay? And since we already learned that impulse is force over time, you can set these two equal to each other. Okay, so these are the 3 equations. You have impulse is force times time, impulse equals your change in momentum, or you can set those 2 equal to each other and say force times time equals change in momentum. Okay? When the force that produces an impulse acts for twice as much time, the impulse is what? Doubled. Okay. So for increasing momentum, you want to apply the greatest force for as long as possible and extend the time of contact, right? So that's why in golf or baseball or tennis or any of those sports, you follow through, right? Because you're extending the time that you're applying force to something. If you bunt the ball The ball doesn't accelerate as much as if you swing and follow all the way through. Okay. A cannonball shot from a cannon with a long barrel will emerge with greater speed because the cannonball receives a greater, does it have a greater force? When you blew on your dart gun, if you put it in different places in the thing, did the force that you blow change depending on where you put the dart? So you blew harder when it was in a different spot? No, the force was the same, right? It's just that in some cases, the dart experienced the force for longer periods of time, right? So it's the same with the cannon. When you have a cannonball shot from a cannon, the force is good. The average force is the same. It's just that, so this is the same. Let's see. It's just that the impulse is greater because the force is applied for a longer period of time. Okay? So the answer to this one is B. The average force on the cannonball will be the same for a short or long-barreled cannon. The longer barrel provides a longer time for the force to act and therefore a greater impulse. Okay, so those are all for increasing momentum. Now you can use impulse to decrease momentum. Okay? So here, I wish I was a better artist, but let me draw this out. Okay, so it says you have a car, you have a fast moving car, and it's moving towards a brick wall. Okay, and there's another one, the same car, it's going towards a haystack. In both cases, so in the first case, the car comes to stop when it hits the wall. And in the second case, the car comes to stop in the haystack, right? Okay, so what's this? Let's say the speed of this is, 10 miles per hour, and here it's 10 miles per hour. And here the speed, once it hits the wall, it's gonna be 0, right? And once it hits the haystack, it'll be 0. So what's the change in momentum for the first and the second one? Is the change of momentum the same? So this is mass times V. Actually, it would be.
Oh, I thought you meant for like the brick wall.
And the haystack, yeah. So is the change of momentum in those the same? It would be because they have the same mass, right? And they have the same final velocity, and they have the same initial velocity.
Wait, why would they haystack? Wouldn't the car go right through the haystack?
Well, it says it's going to come to, so I gave the scenario that the velocity in the haystack is 0 at the end.
Oh.
So that's why I gave the example of like an EcoSmart small car. That makes sense? Yeah, if you had like a tank, it would probably go through it. Okay. So yes, Rob was saying, when the car goes through the haystack, it would if it was a tank. If it's like a small little lightweight electric vehicle, the haystack could possibly stop it. So under this scenario, you're assuming that the car stops in both situations. So assuming the car stops in both situations, the change of momentum is the same, right? If the change in momentum is the same, is the impulse the same? What's one of our equations for impulse? Way back up here. Where is it? Impulse equals change in momentum. So yes, thank you. So yes, the impulse is the same because impulse equals change in momentum. Okay, so if the change in momentum is the same, the impulse is the same. Do they both experience the same force?
No.
No. So that's the difference. So their change in momentum is the same, right? But in the brick wall scenario, the force is really high and the time is small. Whereas in the haystack scenario, our force is small and our time is larger, relatively speaking. Make sense? So the answer is D, no for 1 and 2, or excuse me. It's asking do they experience the same? So just 1 and 2 is correct. So the answer was yes for 1 and 2. Okay, when a dish falls, let's say you have 2 dishes, okay? And you drop one on carpet and one on like concrete. Will the change in momentum be less if it lands on carpet than if it lands on the hard floor? No. Will the impulse be less?
Wait, if they both. Oh, the impulse.
No, the impulse, because impulse equals change in momentum, right? So if the change in momentum isn't less, if they're the same, then the impulse will be the same.
Wait, wouldn't the change in momentum? Oh yeah, the change in momentum.
Yeah. So the change of momentum, whether you drop a plate on carpet or on concrete, the change of momentum is the same. The impulse is the same. What's different is the force and how much time it takes to come to a stop, right? So no. So when a car is out of control, it is better to hit a haystack than a concrete wall. It has the same impulse either way, but the extension of hitting the time, but extending the extension of hitting time reduces the force. Okay, some examples of that. When you jump, do you land stiff-legged? No, because you bend your knees. When you bend your knees, it's extending the time that your body's stopping. Okay, and so that makes a lower force on your body. Another example is in boxing. When somebody, like, if you're in a boxing match and you're getting hit, you want to ride with the punch. That's reducing the force that your face experiences. It's increasing the time, but it's decreasing the force. Make sense? Another example, which is used in the other way, is karate. When they want to break boards, do they go really nice and slow and try to follow through? No, they try to make it really short time so they can have a really high force. Okay? So those are the examples. So what we're going to do next is we're going to do a problem. So if you go into Schoology, there's like an in-class worksheet. Go into Schoology, under homework. You have momentum and impulse in class. Please open that worksheet up. We're going to do that together. I highly recommend that you do this worksheet and pay attention, because the quiz next Wednesday will be heavily based on this worksheet. Okay?
Miss Pena, what's the breakup of the 2 quizzes? Like, how are they going to be like different?
Okay, so Monday's quiz is going to be on momentum and conservation of momentum. So we did a worksheet in class on Monday on momentum, and then you guys had a conservation of momentum homework worksheet. So that's going to be the basis for Monday's quiz. Okay? And then Wednesday's quiz is going to be based off of impulse, which is going to be based off of what we're doing right now and your homework tonight.
Okay, perfect. Thank you so much.
I always try to give you guys an opportunity to ask questions on a concept before I quiz you. So like, you had the homework, today we went over it, and so we'll quiz on it the next class.
Okay, thank you.
Okay, so I want you guys to go to the second page where it says impulse. And what I want you to do is I want you to start solving this. So it starts off with an 800 kilogram car traveling at 10 meters per second comes to a stop in 0.5 seconds in an accident. What was the impulse applied to the car? So what I want you to do is you're going to define the variables, like what do you know and what don't you know? Write which equations apply to the situation, and then try to solve. And then if you think you get that, then you can move on to B. So do that for a couple minutes, and then I'll work through it with you guys.
Wait, where is it?
It's under homework and in-class activities. It's called momentum and impulse in class, I think.
Oh, Miss Pena, F is the momentum, but that's, or the first formula is momentum, but is that what we use for F, the force?
So there's two equations, right? There's, let's see, let me share. Hold on. Just sending an email to somebody. I'm going to share this so that everyone can see this at the same time.
Because like we have the mass and the velocity, so would we just use that to find momentum, and then would that equal F in the impulse equals Ft?
So are you solving A or B?
A.
And what does A ask for? Does it ask for force or does it ask for what?
The impulse.
Impulse. So impulse equals, you said change of momentum?
Oh, I thought it was Ft. That's what it says in the notes.
Well, there's two equations for impulse. Impulse equals change of momentum. Time. And so you can set those equal to each other. You have to decide which of those three equations best fit this particular problem.
Okay.
Okay. Did you get an A and B? Did you get them both, Will? Did you finish? Okay.
Just making sure we're done with this, right?
For what?
Are we gonna go over this?
Yeah. You guys ready to go over A? Oh, I forgot to give out the rewards for winning, right? You're welcome. Was that you? Okay, so let's do A. Define the variables from the problem. So we have the mass is 800 kilograms. We know that initially it's traveling 10 meters per second. We know the final velocity is 0. And we know the time is 0.5 seconds. And we know that we are looking for the impulse. Okay? Next thing we know is we have three equations. Impulse equals change in momentum, impulse equals force times time, or force times time equals change of momentum. So now we need to look and see which equation applies. Well, this equation right here doesn't solve for impulse, right? So we wouldn't use that because we're looking for impulse. This equation here asks for force and time. We have a time, but we don't have a force. So we don't have enough information to use that. Let's see if this one will work. Here, we have a mass, we have V final and V initial. So we have everything we need for that equation. So that'll be the equation we use. Okay? So now we solve. I equals your change in momentum, which means mv final minus mv initial, right? So that's equal to 800. My final velocity was 0 minus 800 times my initial velocity is 10. So that's equals 0 minus 8,000, or minus 8,000 kilograms times meters per second. Why is it negative? Because it's slowing down, right? It's not gaining momentum, it's losing momentum. Okay? Anyone get it? Okay, now for the next one, the variables are pretty similar, but now we have all the same variables except now we know I, right? And we're looking for F. Okay, so knowing that, which equation would we use? So the third, okay, let me write it. So our choices are I equals change in MV, I equals FT, and FT equals change in momentum. We could use the third one, right? We use the third one, we're gonna have to calculate our change in momentum again, which we already did. So that one will get you the right answer, but I'm kind of lazy. So I would rather use this one because I already have the impulse and I have the time and I'm looking for the force, right? So we have I equals FT, negative 8,000 kilograms times meters per second equals force times 0.5. So my force is negative 16,000 newtons. And again, the force is negative because it's slowing it down.